Okay, so thanks to Unesis for the invitation and welcome everybody. So I am Hamza. I did my PhD at IST Austria with Krzysztof Pietrzak, who I see is attending. And now I'm doing postdoc with GL-PoSW at TU Wien. So I'm interested at the moment in working on cryptographic primitives that are related to blockchains. And today I'm going to tell you about proofs of sequentiality for light client blockchain protocols. So Dionys has mentioned that the talk we're going to aim for roughly 40 minutes, potentially a bit more, but so I would prefer a more interactive style. So please interrupt me at any point if you have a question, comment, anything to clarify. It is very strange to always talk to the screen, not knowing exactly if you still have the audience with you or not. So yes, so without further ado, I will start. So this work is jointly done with Georg Fuchsbauer at TU Wien, Bita Gaji at IOHK, and Karen Klein from IST Austria. So light client blockchain protocols, we have two entities, like we have full nodes, taking the part of provers and light clients as verifiers. There's no trust between these two entities, and the light clients would preferably have minimal information about the blockchain, say its genesis, Psi, while full nodes are supposed to be storing the entirety of the blockchain. We would be interested in protocols in which the effort of the verifier is sublinear and the communication is sublinear to make things more interesting. People have studied different applications in this setting. One of the most important ones is bootstrapping. And here's what have been studied so far, in which there would be a verifier talking to multiple provers, not knowing whether any of them actually is holding an honest blockchain, but nevertheless talking to them and wants to end up having a commitment to an honest blockchain up to the last few blocks. So this has been studied in the context of multiple, in a model where we have multiple provers, as we've seen here, and the guarantee is that if one of them is honest, the verifier ends up having a commitment to an honest blockchain. What has not been studied so far and what motivates our work is what guarantees does our verifier have if none of these provers is honest? They can all be malicious, or the verifier can have the chance to read a proof from one prover. What does the verifier have as a guarantee in this setting? This has not been studied as far as we know, and this is the main motivation that this is the main question that we would like to answer. And along the way, we will do other things, other applications of interest like transaction inclusion. Maybe some prover want to convince a verifier that a transaction TX occurred on a blockchain in the ith block, and so on and so forth. You have also the other applications of sidechains in which you are concerned about the validity of events across different blockchains. So the solutions that have been studied, I will highlight mostly bootstrapping because it's mostly the one problem that received more attention, but our work extends to all of these applications. So the different solutions that exist for this problem, one can think of the generic solution of snarks. Snarks solve lots of problems. And you have the very interesting work of non-interactive proofs of work. And you have also fly client. So these are the major three approaches. And as interesting as they are, all of these solutions have some limitations. Some of them, like snarks, require some setup assumptions that we would like to avoid. NIPA-POWs, for example, and fly client, they both have limited applicability to blockchains that run like proof of work blockchains. And most importantly, as I highlighted on the previous slide, is that they all work in a model in which you have multiple provers and you assume one of them is honest. If this assumption is violated, there are no guarantees as far as we know that any of these solutions give you. And what we would like to have is to actually kind of avoid all of these limitations, have something without setup assumptions, and it has general applicability, and it is defined in a way like classical proof systems are defined. So in this work, what we do, we define a classical proof system underlying all of these applications, whether we're talking about bootstrapping, side chains, and transaction inclusions. There's a central entity that we define, and that will be useful for solving all of these applications. But we we focus on the bootstrapping, as I said. So the proof system that we define is called succinct non-interactive arguments of chain knowledge, abbreviated as snacks. We construct snacks from any graph labeling proof of sequential work scheme. And along the way, we unify these graph labeling proof of sequential work schemes. We give a unified definition, we generalize them, and we provide a simple new construction that is a twist of existing constructions, but nevertheless is useful for the setting that we have, and it's very nice to explain things through this construction. The application towards the end, I will see how to use this theory that we developed to actually give a solution to the bootstrapping problem using the snacks. The advantages of this approach that we take is that we have classical soundness guarantees. If the verifier is speaking to a prover, there's some soundness guarantees, meaning if the prover is malicious, there's some quantifiable soundness guarantees that the verifier has. We see this framework as providing simplicity and modularity in the design and analysis of these applications. And interestingly, it allows also for exchange of ideas between the world of proof of sequential work and blockchains. And one of these exchanges is that you inherit a lot of the good things in the proof of sequential work world into the blockchains. One of such interesting properties that if you have incremental proof of sequential work, you get incremental snacks that are interesting on their own. I would not talk much about this element for the lack of time, but in the paper we talk about this. We define incremental snacks and show how they're related to incremental proof of sequential work. So here is the very high-level view of what we're going to be doing. So we are going to construct snacks very simply. We will assume that we will have a blockchain and any graph labeling proof of sequential work. And then we will design an augmented blockchain for which a proof of sequential work proof is a snack proof. Okay, so it's kind of the design is very black box-ish. And pictorially, so we assume that, I will get to these slides in more detail towards the end. Pictorially, again, you assume that you have a blockchain edge. We assume that blockchains are like line graphs with extra edges, and the extra edges here I highlighted as dotted edges. They're like any other edge, but I just highlight them as dotted. And if you're given this and you're given a proof of sequential work DAG, this is one example of them. Then we show how to combine these together and build a supergraph K, and we show how to run essentially a modification of the proof of sequential work on this graph to actually get snacks. So this is the high level on the plan. There are no questions. We can get started with technical details. As I said, I'll be happy to be interrupted at any point. So we're going to be dealing with lots of graphs, and labeling of graphs. And so let's just take a moment to define these objects that we're talking about. A chain to us is simply a line graph with extra edges. It's still acyclic. This is one example that I will be running through this talk. And we will talk about, we label these graphs using some Oracle tau. tau, say, think of it as a random oracle, which what would be the case, sorted random oracles, and you define the labeling in the most natural way, in which, say, forget about the initial case. If you the label of the ith node, you apply the random oracle to the ith index and the labels of its parents. In this case, for example, if you want to label the 5, you hash, you apply the random oracle to the label of 4 and the label of 1 alongside the 4th, and you get the label of 5. So you can label this graph using this oracle. Very natural and well-studied labeling. And this is enough to start actually with the proof of sequential work. I will start with the definition as a simpler definition and then see how to generalize it once and then generalize it twice. So in a proof of sequential work, you will have a verifier and a prover. For the rest of the talk, all my provers and verifiers have access to random oracles, and they will be in the random oracle. So here I denote the random oracle as tau. So it's an interactive protocol, and it's parameterized by a family of DAGs. At the end of the interaction, completeness, the honest prover says the honest prover that makes n sequential invocations to tau, where n is the sequential work parameter. Such a prover make the verifier accept. We would also require succinctness, that the proofs are short and the time to verify them is minimal. All of these polylogarithmic in n, where n will be the time parameter. Okay. So this is for functionality. What do we have for security? So assume that we have a malicious prover now that may have massive parallelism. And what do we guarantee? We define the notion of alpha epsilon soundness, in which such a parallel malicious prover that makes at most alpha n sequential queries for some alpha, say a half or 2/3 or whatever, sequential queries to this oracle, it will fail with overwhelming probability, with probability 1 minus epsilon. Okay. So this is the notion of a proof of sequential work. In particular, if you have like alpha is a constant, in this case, you can make the probability in which a malicious prover convinces the verifier to be negligible. One such simple proof of sequential work that we will see is just another twist of an existing proof of sequential work is the following. To make things concrete, so you have the verifier and the prover, and you have some parameter graph, and this is this is a graph. This is just for simplicity is a graph that has 9 nodes, as you can see. The verifier starts by sending some chi, which the prover will use to solve some random oracle, and will label the graph. This random oracle tau, the prover will use to label this graph as defined here. So it will generate the labels, and in this case generates phi. It's the label of the sync node in this graph, and send it to the verifier. The verifier will then run with the prover a challenge response phase, in which it picks one, say it picks an index I, and then the prover will respond by first defining the path that goes through from the source to the sync through the ith node, and give the labels on this path alongside their parents. For example, and this is repeated enough many times, to exemplify, assume that you have that the verifier picked I and I was 5, as you can see it here in the graph. Then the prover will define the shortest path that goes through 5 from the beginning to the end, and it will give the labels on this path alongside the labels of the parents, to allow the verifier to actually verify the validity of these labels. And the verifier verifies the validity, and it does repeat this challenge response phase enough many times, and it accepts if none of these runs fails. Okay, so this is the simple construction. Of course, this is a simple example that in which you can see that the prover is given almost the labels of almost all the graph, but this is because this example is short. Remember that if you have a graph like this, you will have the shortest path will be logarithmic in the length of this logarithmic in n, where n is the number of nodes here. And for each node on the path, you will have also at most logarithmically many parents. So the whole number of labels that the prover will end up giving to the verifier will be log squared at worst. So this is gives you succinctness, and also the work that the verifier does is very simple and it's also very efficient. Okay. So questions so far? Okay, I hope that things are clear and I'm not talking to myself. So for such construction, we prove the following statement to say if the prover in this initial phase where it's gonna labeling the graph, it made alpha less than alpha n sequential queries to the random oracle tau, and in totality, the first part of the prover and the second part that runs the challenge response phase, if they in total make a number of q queries to tau, then such a prover can make the verifier accept with probability epsilon that is related to alpha as follows. It's alpha to the power of t plus some negligible term. And if alpha is constant and you choose t appropriately, you can make this probability negligible. Okay, so far so good. So this is a proof of sequential work, and almost all proofs of sequential work in the literature that we are aware of, they kind of just define, each one of them defines a different graph and labels these graphs and commits to them, and they follow the same recipe more or less. So the first such construction was by Mahmoudi, Moran, and Badan, in which this upper part, the black part, is dipter-robust graphs. The prover will compute a labeling for this graph, and this orangish thing is Merkle tree commits to it and produces phi, and then you run the challenge response phase with that checks the consistency of labels according to the verifier. The verifier chooses which labels it wants to check the consistency of. And so this construction had theoretically was very exciting and interesting, solved an open problem, but it was very impractical. It is very impractical for many reasons. Cohen Biedjak gave an extremely elegant construction in which you essentially define this graph. You start with essentially the Merkle tree and run a path through it, and it's very efficient and good one, and it implicitly defines phi, a commitment to be the label of the sink. And there's another construction that's called reversible proof of sequential work that achieves an extra property called reversibility that we don't care about in this work. And you can see that the construction that I showed you is exactly this construction, the reversible proof of sequential work, but instead of having permutations and large states, you kind of compress them using a hash function, and this would be more suitable for blockchain applications in which we will see later that each block will store a label of a proof of sequential work label, and here these labels will be, some of them will be large. So this will be not very suitable for that. And there's also another construction of proof of sequential work called incremental by Dotlang, Lima, LaVolta. It's called incremental proof of sequential work that take the CB construction and makes it incremental by a clever on-the-fly sampling. So what I wanted to say from these constructions is that they all seemingly follow the same recipe, and we would like to abstract them and make elements that we care about later explicit. Whatever is implicit here, for example, here the commitment is implicit, here is explicit. We want to make things explicit that allows us to use them in building snacks. So the first generalization that we do is that we talk, instead of some DAGs, we talk about weighted DAGs. So here I still have the thing for a chain, but you can think of it as any DAG, and then you augment it with a labeling function, and you can see here the label for each of the nodes. The takes values between 0 and 1, and they all sum to 1. Okay, so this labeling will allow later to kind of the verifier to choose to challenge the prover on different nodes according to their weight. In the blockchain application, nodes towards the end will tend to have different weight from the beginning, and we will see why this is needed for the snack application. And this is just very natural weight notion. Let me check my time. Okay, that's good. And we also define the notion of alpha valid paths. So we want to talk about, in proof of sequential work, we talk about kind of a fraction of sequential computation. Say you did half of the sequential computation. Now we would want to talk about the path and its weight. So we want to talk about weighted valid paths. This will be a path, and it's labeling such that for each path, for each node on the path, the label is computed correctly, and the summation of its weights is some alpha. Okay, so this is an alpha valid path, is a path whose nodes are valid, and the weights sum to alpha. Very natural notion. And then we will define this language that we will see a lot during this talk. So I will take some time to talk about it. So it's a language that is parameterized by a commitment scheme. It's a position binding commitment scheme, some efficient computable relation R, and gamma is a weighted graph, and alpha is a number between 0 and 1. So the instances of this language will be phi and n. Phi will be a commitment to a weighted graph of that has n nodes. The witness will be a path alongside with some labels and the commitment of the path. Okay, such that this path has some weight alpha. So let's look at it. So this path will be alpha valid. Okay, and with respect to this relation here that we have here, okay, I'm repeating myself, sorry. So this path is alpha valid as we defined it just here, and rho is a decommitment to the path. So if the path has nodes 1 to 5, rho will contain an opening of the commitment of 1 to 5. Okay. So this is the language that we will care about for the proof sequential work, and also for the snacks. The pairs it commits to. It has the commitment of and the length n of the chain, essentially. Good. So now we have this graph labeling proof sequential work. The syntax that we give in the paper is a bit more cumbersome, but I give you the flavor. They're just small steps here. Is that now, instead of talking about DAGs, we right away start talking about weighted DAGs. Challenges here, I'm jumping ahead. Challenges are now not drawn uniformly at random from the set of all nodes n, but they're drawn according to the distribution that this phi n defines. So nodes with higher weights have higher chance of being chosen by the verifier. The second statement, the second message that the first message actually the prover sends will be a position binding commitment to the labels of the graph. So the prover will label the graph and position binding commit to it. And the challenge response phase will essentially be different indices I, and the prover will open a commitment for each I according to this commitment phi, and does some some extra work that, for the sake of presentation, I don't say more than that. So it's mostly, you can think of it as mostly as opening commitments to different indices that are chosen according to the distribution that is defined by sigma n. Okay. Of course, once we start talking about weight, we will have naturally. Please.
Can you give an example of position binding commitments? It's like the Markov tree position binding.
Yes, that's one of them.
Cool. Thanks.
Yeah, welcome. But you can have in the design, you can also have something more generic, yeah. Think of Merkle tree. We defined weight, and now we also define the natural notion of sequential weight. It's a very natural notion in which, if you think of the queries that the prover is asking, are in L rounds. Q1 is the set of all barrel queries in the first round, and so on. Then you take the sequential weight will be the for each round, you take the highest, the heaviest query, and you sum it over all rounds. The details are not that important, but we have to define the sequential weight notions, where it's important for the proofs. And that's all. And then we have defined completeness now in the most natural way. Instead of saying that the prover makes n queries to tau, we say it makes queries to tau that have sequential weight n. Instead of just number n, sequential weight n, succinctness stays as is. And here, one of the other things that we also do, we define a notion of soundness. We want a notion of extractability. So we define alpha epsilon knowledge soundness, in which essentially what you say, for each malicious prover, there exists an extractor that extracts a witness for this language that we define with overwhelming probability. So for each, sorry, I think I'm missing some slides, maybe, yeah, sorry. So there will be for each prover that convinces the verifier or makes the verifier accept, you can extract an alpha valid path according to this language. A path in this graph that all of its nodes are valid, and the sum of the weights is alpha. Okay, and the relation R here is simply the relation that just checks the correctness of labels. It's important to notice this because this is something that we will generalize when we talk to snacks. So this is our generalization to graph labeling proof of sequential work, and existing constructions, because they're in the random oracle model, this knowledge soundness is not hard to actually satisfy. And we show that that existing constructions that we care about, such as CP, also satisfies this notion, because these are the constructions that are practical and would potentially be used. So this is one generalization of our work. We generalize proof of sequential work, and this construction that actually I showed you before is also secure according to this notion. It's a graph labeling proof of sequential work that is secure according to this notion, where you have alpha and sigma. They're just related in this way. So these are just technical details, but I mentioned them for the sake of completeness. And we also show that modified CB also satisfies the same notion. The modification is minimal. We have to add extra edges to be able to challenge on all nodes in the graph rather than on the leaves as is originally done in CB. It's mostly cosmetical change, but nevertheless needed to maintain its security. But they are equally secure and equally good for the applications. We choose this one not for any other reason except that it's just easier to fit on slides and it looks nice, but in practice maybe CP in many aspects will be more efficient actually. So this is the first part, and it covers more than half of the lecture. If there are questions here, I would take them before continuing to the next part.
Just a quick question. Maybe I'm just asking something that you will talk about later, but I'm just trying to fit in my mind how this will work with proof of work and proof of stake. So maybe you plan to extend this relation R to verify this here?
Yeah, that's the next slide. Yes, that's coming up.
Great. Yeah, thanks.
Okay, cool. So one way I would like to talk about snacks as a generalization to this generalized notion of proof of sequential work. And the generalization is very natural and simple. So remember that these are the notions that we talked about: labeling, alpha validity, and this relation. The first thing that we generalize is the notion of labeling. So here, labels, they do not only contain just the labels from the random oracle, but they can contain some arbitrary bit strings. And we call such labeling X augmented tau-based graph labeling. And these X's will intuitively incorporate the blockchain related content in the blocks. So the block will be essentially the XI plus some extra information from the proof of sequential work. You could think of it as it is the snack as extending the proof of sequential work, or the snack is just, yeah, that's a different way of looking at it, but this is the easiest way of looking at it. It's just augmented labeling of a proof of sequential work scheme. And the second important thing that we need is to also like allow for more general relations R. The relation R that we considered before was only checking the validity of labels. While here we also need to make sure that, say, in a proof of sequential work, that in each node, the ith node, it not only contains valid proof of sequential work label, but also valid proof of work. So we need this relation to be able to check publicly verifiable proofs, as is the case in say, proof of work. And if you have also proof of space and whatever publicly verifiable, you can also verify it using this relation R. And we use the exact same relation that I defined here. Okay, and the same notions apply. So now defining snacks is kind of a formality, but nevertheless I will say it. It is exactly this generalization of a proof of sequential work. Completeness says, well, if you computed the proof correctly, then you have a path, an alpha valid path where alpha is 1. It has all the nodes. Succinctness is as usual. And more importantly here, that we no longer talk about interactive proofs. No, it's succinct. The N is for non-interactive, so it's just one proof that the prover sends to the verifier, and this is the relation that over which this proof system works. Okay. Well, I should say also that in proof of sequential work, they're generally defined in the interactive setting, except for the incremental proof of sequential work, which was defined right away for the non-interactive setting. Maybe I said incremental instead of interactive. So I repeat, proof of sequential work are defined in the interactive setting, and then they can be turned into non-interactive using Fiat-Shamir. While the snacks, we define it right away to be non-interactive. Although the way we construct it, we also construct an interactive protocol and then Fiat-Shamir it. Of course, it also makes sense to define first an ACK without the non-interactive part, but it doesn't matter. It's a matter of test. So this is the correctness, and then if you talk about soundness, it's the same notion of alpha epsilon knowledge soundness that we talked about. Exactly the same. Nothing changes. The only thing that changed is that the relation here, instead of checking just labels, it checks labels and validity of publicly verifiable proofs that are related to the blockchain in question. So now, how do we construct snacks after we've defined them? So they're very, now probably you already know. So we assume that we have a blockchain whose DAG is a chain as we defined it here. So it's a path with extra edges, and it has some validity relation R. The validity relation R, it takes an index node I, say block I, and its parents, and it decides that this is a valid block or not. Okay, so in the proof of work in Bitcoin, say the only parent is the previous block, and you take the current block and the previous block and say whether this block is valid or not by checking the proof of sequential work. Of course, one could talk also about transactions, stuff like that, but that's orthogonal to this work. So we assume we have a blockchain with validity relation R, and we assume that we have given any graph labeling proof of sequential work as we defined it, and this is just an example. You can use CP instead of this. Everything works as in the same way. And we would then use this augmented graph that it has elements from both graphs, here GI and HI. And we will see how to actually define these labels, G and H, such that we can run essentially the same strategy of a proof of sequential work on top of this new graph and get a snack as a result. And you can see everything is almost black box, and you inherit all the good stuff from the proof of sequential work and the bad stuff if there is any. So how do we actually augment this? I'm almost actually done with the technical stuff, so bear with me a bit. So this is the graph. How do we calculate it? So this is the algorithm. So there's an initialization phase that kind of deals with the genesis block. We can just leave it aside and look at the mining algorithm now. The mining algorithm, essentially, what you think of it as, it takes a blockchain of, say, it takes some labels of some ith length. So say this is I. It takes, this is the ith block, and then it computes the I plus 1 block. So it gets these labels, which I call them Ki, Kj, which, yeah, tuples of G, and H labels plus Di. Di is the current data. So assume that you are now the miner, and we want to define an augmented mining protocol in which you get a blockchain of some length, and you have a set of data, Di, transactions that you collected, and then you want to produce the next block. So what you do is you compute a label, an intermediate label Li, using the proof of sequential work computation. So you compute a label according to the proof of sequential work computation, although here you look at different K. Let's ignore these technicalities. And then you compute a commitment essentially to the state so far, what you have, the blockchain with the new label here. And then you define the GI label, which will be the proof of sequential work label will be Li concatenated with some commitment, okay? So this is so good for the proof of sequential work computation part. And then now you do the actual mining part. So by I will be essentially, you will find, say, if we're talking about a proof of work blockchain, you find a valid proof of work, okay? That verifies according to this relation. So this relation R will take the GI that we computed, the proof of sequential work labels, plus some HI. This is blockchain related stuff where DI is the set of the data, including the transactions, and the publicly verifiable proof, in this case, proof of work. And also the labels for the parents in terms of the proof of sequential work. The relation does what we said before. It verifies the validity of the proof of sequential work labels and the validity of the publicly verifiable proof of this newly added block. Okay, and it gives the next block here. So this is an augmented mining algorithm that also, you can think of it as defines an augmented tau-based labeling of this graph. Once we have that, we have our relation that we already defined, and the input, this phi n, it will be is the commitment that was output at the end stage of this algorithm. So you can think of the output of this augmented mining algorithm as generating a valid statement witness pair according to this relation. It's not straightforward to see it right away syntactically, but it's trivial. It's just syntactical changes, and you can see that the output of this augmented algorithm gives you a true instance and witness pair according to this relation that we defined. The only thing that we also need to define, so this is kind of the modifications to the blockchain protocol. You need to have an augmented mining that works as follows, and note also that the only addition that you have is that blocks here in the blockchain will contain these G labels, essentially, which are the proof of sequential work related stuff. Okay, and this will be short, like say 256 bits or so. And you also want to augment this validity relation that we started with R, that was the validity relation of the blockchain, and we augmented with to verify the validity relation of the blockchain plus check some proof of sequential work related stuff. Okay, like essentially that validity of labels. So this will be, that's it. So that is the snack that we build. You can see it as just a very simple generalization of proof sequential work schemes. And I also could say something for the efficiency here for this protocol and for actually CP. This commitment part will not be needed explicitly because implicitly they define phi I to be the label of I. So you already, by computing the label, you already computed the commitment. That was implicit in these previous works. We also made it explicit to be able to rely on it in our security proofs. So this is just really the only addition. GI is LI, which is like random hash function computation. That's it. It's very short. And what we prove, of course, this is an interactive protocol. We fiat shamir it and we get an interactive protocol. And we show that the alpha knowledge soundness of the snack follows directly from alpha knowledge soundness of the underlying graph labeling proof of sequential work, which what we think is nice in terms of simplicity and modularity of the design. In the last 10 minutes that I have, I will quickly now tell you how. So this is the snack as an object that we can use to solve many of these problems that we looked at before, namely bootstrapping, transaction inclusion. It becomes kind of trivial now. Once you have a commitment, you just open a commitment in any position you want. Sidechain stuff is also somewhat easy. And we'll show you the bootstrapping thing in the two settings and how to use also a snack as generically to solve this problem. So for this, we need an extra assumption. So I will first show you how to solve this problem in the multi-prover setting, in which we said that we don't want it. We want a classical proof system setting, but we'll come to this in the last slide. So we will rely on assumption that was formalized in the paper of Fly Client. It's called CL assumption, in which for some C between 0 and 1 and an integer L, the assumption is that no adversary can produce a fork of more than L blocks with a valid C fraction of them, except with probability delta. Okay, so this is kind of the assumption that they don't relate it exactly to the security of the underlying blockchain, but there are some works that deal with this, and this is beyond our paper, but we use the same assumption. And remember that snacks, by definition, they're sequential, and they prove knowledge of valid chains that are sequentially computed. And this is intuitively says that once a malicious adversary tries to fork somewhere from the chain, then it has to actually sequentially compute using its own mining resources an alternative chain that is hopefully that is long enough to convince the verifier. So it has to really use its own resources, and it cannot recycle publicly available information due to the strict sequentiality requirement on the snacks, which is what you expect for a sequential object like a blockchain. And this is slide just for completeness. The last part of it is that we follow the same strategy as Fly Client with some adaptation and changes here and there, but essentially it's the same approach. And we define an alpha and sigma n such that no such adversary can create a chain that has weight greater than alpha, and that will. So this is what we do, and this will be needed for applying the snack. this is just the computation, how you do it. It's very similar to Fly Client, and we refer the reader to either our paper or the Fly Client paper, or both to see the details of this. And once we have that, so the last two slides, Pictorially is it assume that you are a verifier and you have a bunch of provers, each one of which has some commitment to a blockchain of some length, so here N1, N2, and N, and some proof, snack proof. All of these are snacks. And then the verifier will receive a bunch of snacks. It will essentially accept the best accepting one of them. Okay, so the one that that tells you that has the longest chain with heaviest valid paths. What you expect naturally. Okay, you just order them in a way and choose the heaviest accepting one, and you accept it. And classically or previously, what people show is that they use also the same strategy, of course. If one of them is honest, say here B2, then you accept the honest proof. Unless, of course, the malicious proofs are better quality. So this is kind of allows you to synchronize and bootstrap. If you have multiple provers and one of them has an honest chain, then you end up having adopted the proof by which will also contain the statement, the commitment to an honest blockchain. The last slide says that if you have a single prover, what do we get? As I said before, we're not aware of any work that does give you any guarantees before, but what would happen in a scenario where you have a verifier and a prover, you don't know whether this prover is honest or not, whatever. It has a chain and claims it's a chain of some length n, and this is a commitment to it. You look at it and you accept it if it's valid, and you reject it otherwise. What guarantees do you have? Well, by definition of the snack, it says that B must know a blockchain with sequentially mined path of weight alpha n, where alpha is a function of n as defined in the previous slide. It's not important, but it's important to have it in mind now. But it's alpha that depends on n that the prover claims to have. So it must actually, but this, although it convinces the verifier that this valid path is computed sequentially, and if it's a proof of work, you know that in each block you must compute a proof of work, which is heavy and which takes time to actually compute, and you can have some estimate of how much time it must have taken this prover to compute this valid proof, but it doesn't tell you anything about reality, about whether this proof relates to the honest blockchain out there. But this is the best that you could do to make the cost of a malicious prover as costly as possible, namely computing a blockchain essentially sequentially. If on top of that, the verifier knows how long is the honest blockchain, like only its length, then actually this prover, this proof that it accepted, it corresponds to an honest chain. So this is kind of an application in which if the verifier knows something about the blockchain, it can actually talk to one single prover, and it has meaningful guarantees that were not formalized before. With this, I thank you, and I hope to answer your questions. Thanks.
Thank you very much for the very interesting talk, Hamza. So let me start with one question, which is, does this apply to proof of stake, and can you have some comments around that?
So the thing is that we construct is generic, doesn't really talk at any point at the proof of stake or proof of space or proof of work, but the guarantees that you would get, would the guarantees be meaningful or not? So, for example, if you apply it in the proof of in the proof of work setting, and you know that the verifier once accepts a proof, the prover must know of an alpha valid path. Okay, so a lot of sequential computation, and you know that each sequential step in this computation is actually heavy. It's computing a proof of sequential work, which may take 10 minutes or whatever the time is that one needs to actually compute it. So you can have some meaningful guarantees that this proof that the prover produced is really costly and heavy. Okay. But what does it mean to have a sequentially computed bunch of signatures, as is the case in proof of stake? So yes, our snack will apply to the proof of stake protocol, and it gives you like an alpha valid path of sequentially computed signatures. Would that give you any guarantee, given that these signatures are very easy to compute? So it's not clear. It applies to proof of stake, but it's not meaningful at all. And how to make it meaningful, I'm not sure if this is the snack could make it meaningful, or you need a different mechanism. But that's a very interesting open question to see how we can actually have some formal stuff and generate such light client protocols for proof of stake. We don't know how to do it.
Thank you. Any further questions?
Comments and remarks are also welcome.
I do have one. I need a little bit more explanation on toward your last slides, one before the last, when the bootstrapping thing. Yes, I'm not convinced that the verifier realizes the honest prover. Can you explain a little bit more if you have time?
So okay, let me try to go through it a bit. I was a bit fast. Here's the verifier, and it will read bunch of proofs, okay? So it will order them in order. It will order them, from the best one to the worst one. So assume that they are ordered like this, that this N1 is bigger than N2, N2 is bigger than N3, and so on. So N1 claims, P1 claims to have a proof, a snack proof for a chain that is the longest, okay? So you read this proof. If it's valid, you accept it. If it's not, you move to the next one. Once you have a valid proof, you accept it, okay? Because you have extractability guarantees. If any prover manages to convince you of its proof, then you know that the prover must know of a chain of that length. Okay, whether it is related to what the honest majority is holding or not, this is something else. So and now, if we assume that one of them is honest, okay, so if one of them is honest, and according to the CL assumption, it will be clear, it should follow from the CL assumption that malicious provers could not generate proofs of chains that are longer than the honest chain with overwhelming probability. With overwhelming probability, they would not be able to do so. And so whatever the verifier will end up accepting will most likely, with very high probability, correspond to the proof that was generated by an honest full miner.
Okay. I think it's clear now. Yeah.
Yeah, I was a bit fast because I feel bad when I was taking too much time. I did not rehearse the talk, so.
It's very interesting, though. Thank you.
Welcome.
Any more questions? Okay, maybe if there's no further questions, I can ask one final question, which is like one of the things that comes to mind, which I don't think this protocol is directly applicable to, is figuring out variable proof of work. So how does this, because like in the case of variable proof of work, the nodes have to contribute differently to the alpha, but in the way you have it, I think it's by count. So could this be extended to account for that, or do you have some comment on this?
Thanks for the very good question. So actually, when we talked weighted generalized graphs to weighted graphs, because we thought intuitively this will also be useful in the variable difficulty setting, our paper is in the fixed difficulty setting, and we have initial results of how to do it for the variable difficulty settings, but this is something that one has to think about separately, yes.
Okay, thank you. Any final questions before we wrap it up? Okay, thank you very much for making the time, Hamza, today. It was wonderful to have you. And thanks for the wonderful talk. So let's thank Hamza. And yeah, thank you everyone for coming today. And we'll see you all next week. Have a great evening and afternoon. Bye.
Thanks, everybody. Thanks.